So Sabetta said she'll join around now. I'll keep an eye on my email just in case.
Oh, here's our guest.
Wonderful.
Okay, let's see. Jason, I'm going to make you the host. There we
Okay.
go. And I already started recording, so that should be good. And you probably will want to make Sabetta co-host so she can present.
Yeah, I'll do that. And I also have to admit people as they come in. Is there a way to admit them en masse?
Yeah, there's an admit all right above, where you see the waiting room. It should be an admit all blue type thing.
Admit all. Wonderful.
But I think that admits only the people who are in the waiting room at that time.
Right. Makes sense.
So,
I'll keep an eye. I assume we admit everyone.
Well, sometimes there's some evil people, I guess.
Yeah, but is there a way to know if they're evil from their
you
name?
should know everybody's name.
I mean, sometimes it's just one name.
I looked up Bailey Burke was the first in, and it looks like that Bailey is an undergrad in our department from what I could tell. So
I can vouch for Bailey.
Okay, thank you. I didn't know.
Exactly. And Sabetta, do you want to try sharing your screen? Just make sure everything's...
Yeah, give me a second.
Whenever you're ready. We start a couple minutes after 4. So. Okay, admit. Yeah, for the most part, I recognize the names, so I'm just gonna wantonly admit.
Okay, can you see my screen?
Yes, it's beautiful.
Yep.
It's a dragon.
It is a dragon. My iPad should be able to run this presentation, but it seems like it's not being super happy right now.
Sabetta, you're in Georgia, is that right?
I am.
Is it nice there? It's all dark and gloomy here. It's raining.
Yeah, the weather's been nice, but politics haven't.
Oh yes, well, there's lots of politics. So we're waiting to hear about Georgia.
Yeah. So is everyone, us included.
no news as of right now.
I doubt we'll hear for another few days.
I'm disappointed in you, Dave. What kind of an Oregonian looks at this as unpleasant weather?
Yeah, right. Well,
Supposed to
it's
be our
our normal
natural
weather
state.
for this time.
Okay, I'll give maybe one more minute because people are still streaming in, and then we can get started. So typically, I'll try to keep an eye on the chat, Sabetta, in case there's questions in the chat that make sense to be answered. And people also typically jump in with
Okay,
with questions. I assume that works for you.
I'll try to keep my eye on the chat as well, but
Yeah. No, yeah, if that, yeah, I'm happy to try and interrupt if there's something there that's that might make sense to address kind of while you're going along. Okay, so what do you think? Shall we get started? I guess I'm the host, so I get to decide. Yeah, I think we have a good number of people in the meeting already. All right, so let's get started. It's a great pleasure for me to have the opportunity to introduce our speaker today. Sabetta Matsumoto is an assistant professor of physics at Georgia Tech. And she got her bachelor's and master's and PhD degrees in physics in relatively short order, I should say, at all of the University of Pennsylvania, following which she moved on to postdocs at the Princeton Center for Theoretical Science and at Harvard University before her current position at Georgia Tech. Sabetta is a soft matter physicist. She works on a wide range of problems involving mainly geometry and topology in soft matter, ranging from 2D elasticity to the physics of liquid crystals and topological defects in liquid crystals, to designing exotic metamaterials, to even to, as we'll hear today, the math and science underlying knitting. Besides material science, she's also an expert on visualizing non-Euclidean spaces in VR. Unfortunately, this is something that is harder to experience remotely, so we'll just have to have her visit sometime in the future so we can try that out as well. And among her accolades, I'll just mention a few. Sabetta is a Cottrell Foundation Scholar. She's a recipient of the NSF Career Award. And she's one of the few soft matter physicists I know, actually the only soft matter physicist I know, who was the subject of a full-length profile in the New York Times about her work on knitting. One thing I want to bring up before for handing over the floor is that one aspect of Sabetta's work, which really stands out, is that her papers are really fun to read, no matter how mathematically demanding or technical they are. And I think we'll see that in display, starting from the title of her talk for today. So Sabetta, welcome, and the floor is yours.
all right, thank you so much, Jason. So I'm going to be telling you about some work that has been done in my group recently. So we're really interested in studying textiles, and in particular knits. So these are some of the most ubiquitous materials we use in everyday life. You are touching textiles almost all the time during every moment of your day. You interact with them via clothing and upholstery, curtains, tablecloths, napkins. And as far as sort of man-made composite materials are concerned, they're really, really sturdy. They're flexible, they're stretchable, they don't wear out very quickly. Since the Industrial Revolution, they're incredibly cheap to make, which is maybe not a good thing anymore, given the amount of pollution that's coming from people throwing old clothes away. But that makes them a really interesting material to study. So I'm going to be telling you two stories today. So I'm going to tell you first a story featuring the gentleman in the middle here, Shashank Markande. So he's a PhD student in my group, and he will be graduating in, I guess, just about 2 months. He's planning on graduating in end of December. So if anyone is interested in an awesome postdoc, he's on the job market right now. And he's the student in my group who worked on the sort of knot theory, sort of more mathematical aspects of this. And then the second story I'm going to be telling you is about the sort of joint work between Mike Dmitriev and Krishna Singhal. And so what they've done is Mike has come up with a bunch of simulations that study the relationship between topological entanglement and elasticity of fabrics. And then Krishna has done a bunch of imaging and experiments to corroborate some of this, but also to sort of show us new phenomena. And so I'd also be a little bit remiss without bringing up the rest of my group. So this is actually not the rest of my group. I've had added 2 people in the last week who I don't have pictures for. So, I have Daria Atkinson, who's a postdoc, and she's going to be looking at moving from sort of the flat fabrics we're studying to fabrics with 3D topography. Brian Day is a grad student who's writing a physics engine for curved spaces and studying swimming in space-time. Louis Campbell is an undergrad who is examining how the geometry of seams give shapes to clothes. Jenny Lin is a visiting scholar who studies the computer science of knitting machines. And then I have 2 new students. Sarah Gonzalez will be taking over the computational on the project that I will be telling you about later. And Aradia will be working on how flatfish swim using sort of traveling waves. So that's sort of my group in a nutshell and all of our sort of various interests. And they're just an incredible group of students, and I'm so lucky to get to work with them. So I guess into this story. So in our group, we kind of have this mantra, and that's knitting is coding. And you can see just by looking at the textile on the left and then the sort of ASCII pattern on the right that sort of encodes the topology of the stitches on the left, this already sort of looks a little bit reminiscent of computer code. But the analogies go sort of a step further than just thinking of this sort of binary processing. And I'm just going to take a little segue and tell you a little story about, this is the Jacquard loom. This was invented in 1804. And so what this is the precursor to all modern day computing. So this is a system that had punch cards that were used to individually address every location in a woven textile. So it basically tells you go to, X57, Y 129, and okay, the yarn is going to cross over there rather than under. And so basically from this, you could pattern in any sort of non-repeating, extremely complex textile, as you can see on the right. So knitting is more complicated than this sort of binary type of patterning for a few reasons. I guess one is that we no longer have things that are digital or bit based. So there's many stitches you can have that function, that act on any given cell, but also cells themselves don't have to be sort of isolated units. You can take a block that has like 7 cells and turn that into a single complex unit. And what those units are tell you some things about what can and can't happen later. So in that sense, it is a lot more like coding rather than just sort of a binary storage system. And so another thing that's really quite interesting about knits, and this I'm going to say is true of knits over sort of woven materials, is that the changes in topology, so each of the little symbols on the picture on the right here are indicating some specific topological move with the yarn. So the exact way you change topology actually affects the elasticity of the textile. And so we really wanted to study what's going on there. And so that's what I'm going to talk about for a little bit. So this is the process of knitting. This is hand knitting. We do have machine knitting as well, but this is a little bit more illustrative as to what the local topology is. So basically you have 2 needles, and they're basically just storing a bunch of loops in your system. And you've got a free strand of yarn, and that's sort of stuck to the back of the right needle. So what you do to take a stitch is you stick your right needle through the first loop in your left needle and pull a loop of the free yarn through it. So basically you're just taking a loop and pulling another loop through it. And in this case, I'm pulling a loop from the back of the fabric through to the front of the fabric. And that's what we call a knit stitch. And that's what you can see in the upper right corner here. This is just a single unit cell of a loop that's being pulled through another loop. If I were to instead start with the free yarn on the front and pull the loop from the front of the fabric through to the back of the fabric, I end up with what we call a purl stitch. So these are really the same thing. They're just related by a rotation of 180 degrees about the vertical axis. And so these form the most common materials that basically probably the most common of all textiles. And this is called stockinette if you're a hand knitter, and it's called jersey if you're a sewer. And I pretty much guarantee you that everyone on this call is wearing something that's made out of this stockinette right now. This is t-shirt material, this is hoodie material, socks are made out of this, underwear, elastic bands, pretty much anything you have that's a little bit stretchy is probably made out of this topology of fabric. So there's another few simple fabrics that are made just with these combinations of knits and purls. So I'm going to just show you the few we're studying. So first you see garter stitch, which is an alternating pattern of rows. You've got knit in one row and then purl in the next row, and then knit in one row and purl in the next row, and so on and so forth. And then you've got rib, which are alternating columns. So a column of knits and a column of purls and a column of knits and a column of purls. And then the last one is called seed. And this is a checkerboard lattice of knits and pearls. And so basically these look like, from the little schematic view, that there should be almost no difference between them. And hold on, I'm gonna stop screen share for a minute and hold up some samples so you can kind of see them. It turns out that just this topology change of whether or not I'm pulling a loop from the front to the back or the back to the front has a really profound effect on the elasticity of fabrics. So this is the stockinette, the sort of original fabric, and this is stretchy. It's pretty resilient. I guess the most interesting part about this fabric is that it's not flat. It sort of curls forward on the top and the bottom, and it curls to the back on the left and the right. So that's interesting. I'm not going to quite go into that out of plane aspect in this talk, but it's something that we're interested in studying. So the next sample was garter. I should say stockinette and garter are actually named based on their elasticity. So stockinette is named after stockings. And so these want to be kind of a little bit firm, will stretch over your leg. And then garter is for garter belts. So this is less stretchy in this direction, but really quite stretchy in the Z direction, or the Y direction, depending on if you're teaching freshman or higher level physics, I guess. So this is something that is also interesting to note, is that these two samples were made with the same number of stitches across and the same number of rows up and down. So you can really see a striking anisotropy coming from the aspect ratio of the two samples. And to even further that, this is the one that's rib. So this is like half the width of the other ones. And so this is alternating columns of knits pearls. And this is almost accordion-like fabric. It's really, really stretchy in this direction and not so much. It's sort of very mildly stretchy in this direction. And this is used, so it's probably the second most commonly used fabric. So probably a lot of you are wearing something made out of this. So t-shirts, the collar of cuffs of sweaters, cuffs and socks, they're often made from this pattern because of that extra elasticity. And then the last one we have is...
Can I ask a question here?
Oh yeah, please.
Yeah. So you've been talking about the topology, but there's also geometry here, right? So the overall scale of a knitted piece of fabric presumably is something you can control by controlling the size of the loops you make, no? Or you
somewhat. So these are all made with exactly the same sized loops, the same yardage of yarn, same size needles, same number of stitches, same number of rows. So these are really controlled in that way.
What about, can you change sort of the aspect ratio of an individual loop?
You cannot. That's going to be something that comes from relaxing the system. So if you make a loop bigger, that's going to sort of overall affect it, but it's not going to change the actual aspect ratio. I guess the last stitch or the last fabric I have is seed. So this is something that I guess I really like it a lot. It has kind of a nice texture to it. I like it in scarves and things like that. It's a very sort of middle of the road fabric. Like it's stretchy. It's sort of a bit more stretchy than the original stockinette, but it quite retains it. Pardon?
Was it the checkerboard pattern? Just to
this is the checkerboard pattern. Yes, this is a checkerboard pattern. And this one's a lot more sort of middle of the road than the other ones. Like it's more stretchy this way than rib is, and more stretchy this way than garter is. It's, or about as stretchy as garter is actually. So these are sort of the properties of the fabrics and some of the reasons why these fabrics, I guess, were invented in the first place. So let me go back to screen share. So we were really interested in what it is about these sort of the changes in topology that give rise to this elasticity. And so I'm really going to be splitting this talk into two sections. The first one is going to be very much on topology. We're going to think from the point of view of knot theory and kind of try to motivate what things are you allowed to even knit. So what is the, almost from the point of view of an alphabet or a language. So what are the words you're allowed to use and what is the grammar you're allowed to use to connect them. And then the second half of the story is going to be looking at this elasticity. So looking at what interplay this particular crossing topology combined with some geometry has on the overall effect of the overall effective elasticity of the fabric. So, okay, so this is the, so this is sort of the naive physicist thing. So we said, okay, well, all of these are periodic. I assume the textile is infinite. So I'm gonna, find some unit cell and apply periodic boundary conditions. Pretty standard thing. But then it turns out that when I went to do this, the way you sort of connect up the boundary conditions seems to matter. And that kind of goes against what most of our physicist intuition is. So I guess let's look at the little periodic boundary conditions in the upper left corner. So imagine first I take the left and the right side and I glue them around behind the sample. Then I take the top and the bottom and I glue them around behind that. So I have this sort of thing that has these Dumbo ears now. And so you can imagine me taking either side of these, pulling them up, untwisting them, and then sort of shrinking this back down. And I end up with a loop. This is an unknot. I can untie it. It's just sort of a tangle. And then on the right side, I take the left and the right side and I glue them around in front first, and then I take the top and the bottom, and then I glue them around behind. And now if you stare at this for long enough, you can convince yourself that no matter how I manipulate this, I can't untangle this. So this really is sort of mathematically what we would consider knotted. And it turns out that that we, our sort of naive physicist view of just applying periodic boundary conditions, we made a little mistake. And the thing we forgot is that because there are crossings in the system, there has to be just a little bit of thickness. I need to be able to define something passing over something else. And so the space we're looking at isn't actually just a torus, it's a thickened torus. So really, all textile knots live in the glaze on the surface of a donut. And so what I can do is I can sort of construct this manifold, this sort of thickened torus by imagine I have like all of space, and then for convenience, knot theorists do things in S3, so which is just imagine it as R3, but there's sort of a technical detail that in R3 things are infinite, and in S3 there are no boundaries, so it's just a little easier to do calculations in. But So I'm gonna have that written, but just imagine that it's R3. So just 3-dimensional Euclidean space. So imagine I have a little worm, and I put the worm on the inside of my donut so it eats out all of the cake bits. And then I have one that's in all of empty space, and it eats all of space except for this donut shell. So I can kind of imagine doing that by putting that little worm on these two loops, on the red and the green interlocking loops here. And this is called a hop link. But if I put my worm on those, then I sort of have it sort of eat those out, those rings out, I'm left over with this manifold. So now I can start adding knots to it. And so what we do is, imagine now this is my sort of two periodic knot in the sort of torus where the green sides are identified and the red sides are identified. And at the end of the day, there's a black line that's at each of the 4 horizontal edges where the red and green sides meet. So all of those have to match up to one edge. So I'm going to show you how to put this little chunk of a donut into, or this little chunk of knot into that space, and really glue it up. So here I've put it into the space with the red and green hop links. So I'm going to glue the green sides together so that they wrap around the green loop. So that looks like this. And now I've sort of pulled the green loop over so you can see it all. And so now what I want to do is I want to wrap the red sides together around the red loop. So I'm going to sort of pull the sides up first, and then sort of wrap them all the way around behind. So now I have this structure here. So both green sides turned into a single annulus when they got glued together, and both red sides turned into a single annulus when they got glued together, and they're connected by a black line. So that sort of checks our box saying we did the gluing correctly. But now we're left over with this knot that's sort of entangled with the hop link. And so basically what we have left over, so if I sort of put this into a planar diagram, is I've got a whole bunch of gadgetry around the outside, and then this little dashed line surrounding something that looks identical to the thing I started with. And so this is just putting my knot into a format that's really easy for knot theory to handle. So there's software where I could input these structures in and learn about different knot invariants and all sorts of things that knot theorists are interested in. But one of the questions we're interested in is, what can I even put into this dashed line? What are my choices? Are there things I can't do, and why? So these are the sort of questions we're looking at. So Shashank one day, I guess he'd been playing around with these knits for a while and had noticed that all of these textile knots, these knitted textile knots, seem to have this property that they're what's called ribbon. And that's a fancy way to say that, like, imagine I took the knot and I dipped it in a soap film so that the boundary of the knot sort of is the boundary of that film. And then I'm only allowed to have what are called like ribbon intersections. So the whole piece of ribbon has to pass through another whole piece of ribbon. So I can't have like a partial meeting of them. They can't, the discs can't be sort of sliced open. They have to be cut open only in their interior. So kind of like this. And so he was sort of thinking about this, and then I guess one Saturday I was going to go out for a run, and he texted me this picture in the middle. So is this a counterexample to all ribbon knots being knittable? And so I sort of looked at it and I was like, well, I think I can knit that, but I don't know. And I was like, so I sort of texted back and I'm like, well, number one, what are you doing in your office on a Saturday? Like, this is obviously the whiteboard in your office. I recognize it. You know, go outside. Your office is in the basement. Enjoy the sunshine. And then I was like, I'm not sure if I can knit it, but I'll think about it. So I spent my run like kind of thinking about how to like manipulate the yarn and the needles and everything. And eventually I was like, okay, I think I know how to do it. So I got back from the run and texted him and I was like, okay, on Monday, bring knitting needles and yarn to group meeting and we'll see if we can make it. So he did. And we were in fact able to make it. So it's the fabric you see on the right. And this is now called the cow hitch stitch. So this is a story about how just understanding the principles of math, my student who had not knit until he came to graduate school was able to come up with a brand new stitch that no one in the textile world had ever seen before. And I think that's just, I mean, it's just it makes me really happy. I think it's a really fun thing that math can give back to a centuries old discipline.
Sabetta, does this stitch have any useful properties that the familiar stitches don't have?
This is not a very useful stitch, no. It's kind of decorative. It adds like this little kind of like poof to the side, but it's not something that would have many interesting elastic properties. It might be a place where like, depending on how you make it, it might make like little places that are extra stiff throughout. But the other problem is this is something that you cannot make on a knitting machine. So even making it at an industrial level is not super feasible.
That's interesting. So I was gonna ask this later, but since you brought it up, so is the space of things that you can knit by hand bigger than what's knit in machines? I would have naively expected the opposite, but
yeah. So the space of things you can make by hand is much, much bigger than knitting machines, but it's a quantity that there's not a way to qualify can and hands in that sense. So there's like lower bounds on things, but there's no upper bound at some point, because this is a complexity question. At some point, someone may become dexterous enough to do something that I would find impossible for my hands. That doesn't necessarily mean it is impossible for my hands, but it might be impossible for my motor coordination to do. So there's a little bit of confusion there. And I will get to that, I think, in the next couple of slides. So question about what can be knit, we're going to answer as such. This is back to my periodic boundary conditions picture. So they are interchangeable by sort of chopping stuff out and gluing them into that other picture appropriately. But so what I've done here is I've started off with like M loops, just regular closed loops along the bottom. And I've kind of slid them partially off the periodic boundary condition cell, and they sort of come back on top. And then I'm gonna sort of glue everything down in the gray region. So for now, I'm just not allowed to touch anything up there. And then I have N horizontal lines. So these are going sort of along the longitude of my torus. And so what am I allowed to do? So I'm allowed to do what are called Rittmeister moves. So there are 3 ways that you can change the projection crossings they sort of like two-dimensional projections of knots where you can either remove or induce crossings or topology changes that do not change the topology of the system. So there's 3 of them. So the first one is sort of twisting something and untwisting it.
Did the speaker freeze just for me or for
Yeah.
everybody?
Nah, it looks like Sabetta is
First
frozen.
to me as well.
Hopefully she'll come back.
Aye. Oh my God. It might be worth.
Yeah, let me see if I can.
Might not realize that she's frozen.
Yeah, exactly.
While we're waiting, I was curious if anybody's made a knitting machine that's essentially mechanized hand-like objects or robot hands.
Yeah, I wonder what the space of knitting machines is. Okay, I'll keep an eye on the. Oh, she might have.
Hello, I think my intro
Oh, there you are.
off. Sorry.
Okay, well, we can hear you again. That's great.
Okay. What was the last thing you heard me say?
You're explaining the first Readermeister move, kind of crossing and uncrossing. I think
Oh, okay.
the last thing I remember saying.
Okay. So the first Readermeister move is basically you take a piece of yarn and you sort of twist it up or untwist it. The second one, you take 2 strands that are curved and you can either cross them one on top of the other or the other on top of the first. So you can sort of cross these back and forth. And then the third one, you start with an X with 2 pieces of yarn or 2 segments of line. And then you have a third that you can slide back and forth across that, the X-shaped crossing. So these are the things you're locally allowed to do that don't change the topology. So I'm allowed to do just as many of these as I want in whatever combination I want. And then the next thing I'm going to do is something that's called band surgery. So basically, this is something that happens in knot theory quite frequently, is people do this thing where you take a little rectangular band where like opposite sides are on the knot, and then the other pair of opposite sides are not part of the knot. And basically you switch them. So the ones that were part of the knot originally get deleted, and the ones that weren't part of the knot originally become part of the knot. So this is sort of an example of what would happen over here. So I add the bands, and then after the surgery, this is what it looks like. So I'm going to do that process. I'm going to do it across the little gray strip where I glued everything down. And so when I'm done with that, I end up with something that is now a knotted configuration. So this cannot be untangled. And this is basically the process of anything that can be knit. So anything that can be knit can be described this way. However, it's possible that this describes things that cannot be knit. But again, there's this sort of hazy line of, there's this upper bound of what complexity and can mean there. So if we were thinking about things in terms of a knitting machine, then unlike the very high dimensional configuration space of my hands and my hands plus needle, there are really only a set number of moves that any machine can do. So what happens then is you can basically turn strings of those machine motions into your words and glue them together, and that sort of forms your grammar. Here, we sort of take these sort of units, we call them swatches, and then there's rules as to how these swatches can be glued to one another. So that's a way to sort of enumerate everything that can be knit. So because of this, we're allowed to consider many more complicated things. So these are things that look like they have additional topology generated from playing around with the topology. So I have something that looks like a braid on top of a knit, or this sort of basket weave. And so these are things that really are fundamentally more complicated than sort of the strict unit cell picture I had at the beginning. So in order to do a braid, I have to have some action that goes across many, many, many loops, and it swaps the order of lots of them. And so these are things that we can express using our swatch language that you couldn't express using other forms of sort of pixel-based languages. So I'm gonna spend the rest of my time going over the sort of idea of emergent elasticity. So this is, so we talked a little bit about what we're allowed to knit, but then the question we'd like to ask is, well, why is it that topology changes influence elasticity? And so this is a story that Krishma Singhal and Mike Dmitriev have been working on. So Krishma has made all of our fabric samples. So here's just an image of her making it on this knitting machine is sort of a copy of a machine from the 70s. It's all manual. We're in the process of purchasing a computer-controlled industrial machine now. So this will be a lot easier for her, but she was able to do all of the samples we're interested in on these, on this more primitive system. So basically what her experiments look like they're just uniaxial strain experiments. So this one doesn't show it, but she's put little tiny pins in throughout the actual piece of knit, so she can use computer vision to track the whole like non-affine strain tensor throughout. So the other half of this story is the simulations. So so this is what Mike has been working on. And so he's simulated these knits by thinking about, there's sort of physically two parts of each knit. So there's parts where they cross over each other, so where one piece of yarn is interacting with another piece of yarn, and then there's sort of a piece of yarn that connects those two regions together. And so so what he's done is he's taken these and puts them inside a simulation box. These have periodic boundary conditions. So you fix the total length of yarn in the curve. So this is sort of equivalent to setting the size of the knitting needles you're using, or setting the tension on your knitting machine. And then we use a really simple energy. So this is just energy for an Euler elastica. So we've got sort of curvature squared and sort of the energy density, and that's scaled by some bending modulus. And then you could imagine putting in something that's sort of torsion squared times a modulus for twisting. Turns out that the modulus for twisting is so much lower than everything else in the system for actual yarn that we can neglect it. But it might be important if you're looking at non-spun fibers. And then the last thing we do to ensure that we have the topology is basically we thread a potential down the backbone that it's sort of, for us, this is a Feeney potential, so finite extensibility spring pretty much, that has an effective hard core inside. And so this is something that we do our best to measure on the actual yarn. And then also we measure the bending modulus and the total length of yarn in the curve. So these are sort of parameters we can put into the simulation. And then what Mike is actually doing is, instead of doing kind of a standard bead spring model, we started out looking at what are called Bezier curves. So this is basically a way of doing a polynomial expansion for a continuous curve. So the easy way to sort of understand this, it's sort of it's a very geometric structure. So imagine that my curve is the one in blue with the thing that says central curve pointing at it. So what happens with Bezier curves is you have the lowest order of them. So third order has 4 control points. So the first 2 are the start and the end vectors of the curve. And then the difference between the start of the curve and the first control point is the tangent vector at the start. And the difference between the end of the curve and the third control point, K2, is the tangent vector at the end of the curve. So basically, we can expand these to higher order, and then you'd have curvature defined and higher order pieces. So you can imagine this converging to a real continuous curve. And so he implements these at crossover regions with a 180-degree rotational symmetry, and then he implements them at the connecting regions. And then there's constraints at the start and the end that the locations have to be the same, the tangents have to be the same, and the curvatures have to be the same. And so those constraints basically mean that you need 7th order Bezier curves. It turns out that when we did the calculations, they took a lot more time, but basically did not change the result from 5th order. So all of the results I'm going to show are 5th order Bezier curves. But the results do agree with the higher order ones. So here are sort of the relaxed configurations of the 4 types of materials. So I've got stockinette, which is just the regular knit stitches. We've got garter, which is alternating rows of knits and purls. Then in orange, we've got green is rib, so that's alternating columns. And then seed, which is the checkerboard lattices in purple. So these colors are going to label these different materials throughout the rest of the talk, but they will have their names associated with them. So what's going on here in the simulations are he applies an external.
Can I ask a quick question?
Oh yeah, please.
So if I understood correctly from, I think it was 2 slides ago, you're imposing with the Bezier curve certain kinds of symmetries, because you're basically making an assumption that the forces and whatnot on the box are going to lead to like, for instance, mirror symmetries within the box. But there are lots of examples where elasticity produces symmetry breaking, and so where you can imagine like something gets like weird and not mirror symmetric within your box. So does the modeling you did kind of confine it to only the symmetric operations that happen in the, or deformations that happen in the box, or are you allowed to have non-symmetric things occur?
So these are done assuming symmetry for the most part. So by symmetry, the crossover regions, since the forces are reciprocal, they're assumed that the curve going this way is just a 180-degree rotation of the curve going this way. And that's implemented in this set of simulations, and it sort of makes sense for this set of fabrics. That's not true for all possible fabrics and all possible knots. So that's definitely something we're gonna break in the future. This does chop down the computational time.
Yeah, the phase space. Yeah.
So that's primarily why we did it. It doesn't see, like, these results end up being really close to what you see in the experiments, and in the experiments you also don't see symmetry breaking, so it seems like a reasonable assumption.
Seems reasonable to me too, so yeah.
Yeah, I mean, I'll talk a little bit about, well, ask me about friction at the end if you're interested. We've completely neglected it, and and you might think this is crazy, but I do have justifications as to why. So if you're curious as to why, ask me at the end. But so I guess the simulations, basically, he applies a force to the simulation box, and then allows the box shape to relax as it sees fit, and then looks for the minimal energy configuration. And I think his newest code has some sort of simulated annealing in it as well. So basically this is what the code does. And so here are the results. So the solid symbols are the experiments, and the open symbols are the simulations. And then let me tell you how to read this. So the right half of the plot is kind of what you would think of as your normal stress strain plot. So what I'm doing is I'm applying a force in the x direction, and then the right half of the plot is looking at the strain response in the x direction. The left half of the plot is looking at the strain response in the y direction to a force in the x direction. So we've kind of just conglomerated those together. And so I guess the most notable part of this simulation is that the rib is the stretchiest. So basically the slope at the origin, and for low strains, the sort of linear regime tells you about the linear elastic response. And so for rib, it's by far the stretchiest. It has the lowest modulus, and that's what we would expect. The other thing to notice is that everything sort of diverges, or appears to diverge, with very high stress. So I guess we see similar things in the y direction. I guess in the y direction, I should say, garter and seed are equally stretchy in the y direction. And stockinette, the sort of t-shirt one, is by far the stiffest in both the x and the y directions. So this is showing that our simulations match quite well with the experiments, at least as well as they can with inputting the measured experimental parameters. So what's going on here? So basically what we're looking at here is a plot of the curvature of the knit as a function of arc length. And then the sort of joy plot is showing the whitest ones have 0 applied force, and then the very purple ones have a high applied force. And so the color intensity is tracking the amount of applied force. And so what you see is that that as you increase the applied force, you end up with these regions that are really sharply curved. So these are sort of forming these little clasps in the yarn, and they're pulling against each other, and they're basically connected by straight regions. So all of the strain in the system is sort of concentrated at these crossover regions, and that happens whether you're pulling in the X direction or in the Y direction. And so what we said is, okay, so there's like a bending length to the system. So that's a sort of characterizing how wide the that sort of region of high curvature is. And you can set that by just looking at the energy. So in the low tension, so you basically get a bending length that's a ratio of bending to tension. So at low tension, you have a large bending length. And then in high tension, you have really short bending length. And then so basically we did a little Elastica model where I have some curve with some tangent vectors at the start and the end, and then I apply a force that basically moves the end from some distance r to some larger distance r. And you can see how the so you can see the energy scales as 1/1 minus r over L being the total length of that loop. So this is sort of one way to motivate this energy. So this is the energy in the high tension limit, and that's going to couple that's going to be added on to the low strain regime. So basically we end up with a low strain linear regime that's governed by topology, and then this high strain regime is actually governed by the material properties of the yarn, so how compressible it is, and things like that. So I guess going forward, we're sort of looking at extending this to a full sort of tensor model. So this is an image that's showing, these are the tracks of the pins in the experimental sample compared with an example of a continuum finite element simulation coming from these constitutive models. So this is something that we're working on currently. So I guess in the future, we're sort of interested in playing around with the fact that these knits really are a crystalline structure. And with all crystalline structures, we can add defects to them. So I can add either dislocations or disclinations. And these change the way that the fabric lives in three-dimensional space. And so we're interested in looking at those and how they change both in plane and out of plane strain behavior. And maybe we can use them as things like waveguides, or we can direct stress away from sensitive, I don't know, electronics or things like that. So I guess I'd like to thank all of you for your attention, and of course, thank my students for doing such a wonderful job in their work.
Awesome. If you can, please unmute and clap so that we can thank Sabetta for her talk. All right. Yeah, we're just on the hour. But, we lost some time in between to
Yes,
technical.
sorry, my computer crashed there.
So yeah, but I'll you don't mind if we stick around for for questions. Those of you have a few more questions, I'm sure. So I would be happy to take them now. I had written down, and you said we should ask so what about friction? Because it would seem like any yarn that I think of as this fuzzy, floopy thing, which isn't it catching with everything nearby, or?
Yeah, so all of these completely disregard friction. And so I guess I will make a sort of an argument that's based on empirical observation, is that so you wear a t-shirt, you wear socks hundreds and hundreds of times without them plastically deforming, which means that no matter what, you're not losing energy, any of this elastic energy to the system via friction. So that's so like this sort of sliding friction. The other argument I'll make is if you sort of look at these crossovers, the main thing that you're seeing is sort of tightening up of basically concentrating curvature in those areas. And you're not seeing and like slipping past each other. You're not seeing other things. You're really just seeing these areas sort of roll and tighten up. So I guess you might then say, okay, well, they're rolling a little bit, so that's going to be some static friction. But since the torsional coefficient is so small, it's probably negligible.
I was going to actually ask about that on the earlier as well, about friction. And I guess not only is it plastic deformation, but also hysteresis. Like if you took the piece, stretched it, and then quote unquote adiabatically unstretched it and kept doing that, you might see, lags in the stress strain curve due to the internal friction of the element.
Yeah, so you definitely will see a lag in the relaxation time. But it does seem like it ends up pretty much at the same state with the same elasticity. So the one place that you would see lag in the stress strain curves, if you're looking at hysteresis in that way, comes from the fact that yarn is fuzzy. So you do end up with far away pieces entangling with others. So if it hasn't been stretched in a long time, the two parts of the knot might end up geometrically further apart, despite the fact that the arc length between them remains the same. And so that's one place that you do end up seeing a lot of this hysteresis. And this happens if you're knitting by hand, this really happens in the knitting process because your hands are sort of constantly touching all parts of your sample. It also happens more frequently with animal-based fibers, so wools and things like that. They have those fibers have sort of a cuticle on them, so they end up barbed, so they can like really hook into each other well. If you have something that's made out of cotton or silk, I guess silk is an animal fiber, but it doesn't have barbs on it. I guess silk, cotton, bamboo, things like that, those don't have those barbs, so they tend not to have that sort of entanglement factor. So like none of the sweater shrinking in the dryer.
I have a question. Thank you for the talk. It was really interesting. The question is, you were saying that you can think of these knit patterns as crystals, and then think about all of the interesting things you can do with crystals. If you go to the extreme, is there a well-defined way of imagining a perfectly defect-full system, so a totally amorphous or non-crystalline knit system. And do you have any ideas what the mechanical properties of that would look like?
Yeah, so I guess, so adding in disorder is a really interesting question here. So there are all sorts of senses in which we can add in disorder. So imagine that each of these fabrics is like an Ising magnet system. So I've said like a knit is a spin up and a purl is a spin down. And so this was like, you know, my ferromagnetic sample, and, you know, I have like diamagnetic samples or whatever, things like that. Yeah. You can imagine that I add in disorder to that. And then, you know, so I might end up with, you know, disorder on the scale of each individual spin, or I can end up with places that have disorder that are on much larger scales than an individual spin.
But then you could also imagine disorder in the lattice or deformations of the lattice itself, right?
So adding disorder into the lattice is interesting. So, I mean, I can add in sort of standard defects. I can have things like dislocations and disclinations and inclusions. But the thing that I can't do easily is change the orientational order. So instead of it just being lattice sites, I also have some sort of vector associated with like where my loop is pointed.
Yeah.
So that's something that, so I can have sort of like localized defects in that, but I don't really have global ability to change that. Like I can have very specific places where it's ill-defined, but it's not something I could necessarily do. I mean, I could kind of go like this if I were making lace a little bit, but I mean, it still kind of has this pattern that there is a back and forth zigzag to it. So there's kind of going to be no way I can get rid of that order. So we'll have anisotropy coming from that no matter what. Adding in disorder to the rectangular structure, I can, so it's a thing that, this is one of those weird things where can is an iffy question. So a human who's sufficiently good at following instructions could do this on a knitting machine, even though it's capable of doing each of those individual manipulations. If I tried to do a large random sample, it would probably get tangled or jammed somewhere. So that's an interesting question, because there is always going to be an anisotropy coming kind of from that like vector orientation degree of freedom, but you're sort of maybe going to break up the idea of having anisotropy coming from the fact that you have these sort of rectangularly coordinated units. My guess is that the anisotropy coming from sort of the structure would win out. But I don't have, other than having knit most of my life, I kind of have some intuition of how yarn works, but I don't have any mechanical intuition as to why that would be.
Okay. Well, thank you. It's fascinating.
Thanks.
We do have a raised hand in the.
Sorry, yeah, I had a question. So in this analysis, or
sorry, somebody had a hand raised. Do you have your? I know you're not. Trevor. Okay, go ahead. You can go ahead, and then Trevor can go after Uriel. Is that okay?
So yeah. Who goes first? Oh, sorry. Thank you. For the first analysis, like you looked at like an infinite sort of lattice, right? But in real systems, like you have the edge, right? So how does the edges, like how do you deal with the edges? Like how does that affect the system?
So we've mostly ignored the edges in all of our analyses so far. As far as sort of bulk properties, they're probably not going to make much difference, I guess, in the sense that, you know, they're like far away from the boundaries is sort of most of fabric. They matter in practice because the boundaries are areas that end up having a little bit more yarn than others. So they're a little bit thicker, so they're a little bit stiffer. And so they'll add some extra sort of internal strains to the system, likely. Another place where boundaries are really interesting is when it comes to like this type of material where it doesn't want to stay flat. So having boundaries here is a way to sort of relieve some of the internal stress that comes from the fact that this doesn't have a mirror symmetry or a rotational symmetry about this axis, whereas all of the rest of them do. So that's a place where boundaries are really interesting. Another thing about boundaries from the sort of topology point of view is that when we assume that we're in this infinite periodic structure, I can make a well-defined knot. If I have boundaries, then I have these free curves. And so there's not a great way for me to talk about what entangled means, since mathematically an end can just be like threaded through the whole system without paying a cost. So when I'm quantifying entanglement, I'm doing so presuming that I have some knotted structure, and sort of locally the structure stays knotted. I guess the flip side of that is there is that sort of saying where you can pull a thread and your whole sweater unravels. So there is a truth to that, but it's not quite as easy as they make it sound. So normally if I were to just cut these boundaries off, it's not gonna fray, it's gonna look virtually identical to this. It'll hold together really well, which is not true of woven materials. So in that sense, I could have different boundaries, but if I had just pulled my needles out of a sample, so I have the specific boundary that has only these loops, and I pull the free end of that, then it will unravel the whole thing if I pull for long enough.
So my more technical question was going to be about the edges of stockinette, which I think you just answered. So a knitting related question, for the, I can't remember what you named the stitch. Have you found other stitches like that? And two, is there a place where I can see patterns on how to actually do that? Because getting the yarn to loop in that way, I can't think of how to do.
Yeah, I kind of, yeah, it's not a super easy thing to do just with needles. Like I kind of used my finger a little bit to hold it in place. So I guess it's, I mean, the knot theory, so we called it the cow hitch stitch. So there are any number of other things that are similar to that you can do. Basically, most of this comes from make a really big loop, do something cool with the loop, and then knit into it somewhere. So it's kind of the idea, like knitting idea behind that. As far as directions to do it, we haven't really written anything up. There's like a little bit where I did it in a number file video that's maybe going to be edited, but But yeah,
Cool. Thanks.
Awesome. Are there any more questions for Sabetta? All right, thank you. Well, I can wait. I've been told on Zoom you should always wait a little longer than in real life. So I'll wait a few more seconds. And then, but otherwise, yeah, thank you very much. And thanks for staying over. It's late there, I know.
yeah, thanks everyone for sticking along and asking questions.
Yeah, let's, so if you're around and you want to unmute to thank Sabetta again.
Thank you.
Awesome. Ben, did you want to, yeah, I heard you didn't talk very much about the Hopfions, but maybe you'll have to find another time.
Yeah, we talked a little this morning, but
Yeah.
yeah, talked about more fun stuff.
Yeah. Cool.
Yeah, it was very fun chatting with you.
Yeah. I did have a question. So you mentioned kind of this rectangular type of connection unit cell. Are there alternatives? Are there like hexagonal or trigonal, or they? I guess you always have a base kind of strand. You then go back and forth. So.
Yeah. So I guess I can share screen for a second again. So this is, if you look super closely here, you kind of end up with I guess this one, it's hard to tell if it's octagonal or hexagonal here. There's a few things like this. There's one that gives you better kind of honeycomb structure. It still is kind of based on going back and forth, but you're alternating, kind of making sort of these zigzags.
Okay.
So you definitely can do that to some extent. You're still going to have like a preferential direction, but I guess that's consistent with honeycombs, is you have sort of a direction that all of the faces are sort of flat stacked.
Okay.
Yeah, I was wondering about that as well. So the constraint is, I guess, you have this one thread that has to make its way back and forth. If you include multiple, is there any sense in which you could like add more strands, and that lets you do things that you couldn't do by just coming back?
So there's definitely types of knitting that do use different numbers of strands. So I guess those are consistent with our definitions of that sort of swatch thing. And there's definitely things that you can do that you couldn't necessarily do with like the single strand knitting. There's some sort of cool patterns that are sort of, that you have sort of like a front and the back to. There's definitely a lot of things that are based on colors that you really use the interplay between the stitch topology and like the strand. So like here I have like, I've got like V's going across it. If I flip it over, I've got like a double green line, and then there's two white stripes in between. And this one I've got like a dashed green line and a solid green line. So you can sort of play around with like color patterns a lot that way. It's maybe not so much from the physics point of view, but it's really fun from like the design point of view.
And you had mentioned 3D weaves as well. So does that look completely different from this, or is it kind of adding a dimension to this in some sense?
Yeah, so I guess so 3D weaves are kind of crazy. Like there are looms that will make like 3D blocks of material. I guess from a knitting point of view, we're still mostly sticking to the like thin shell approximation. So if it's thin, then you have like it's easy to see a lot of curvature. So like, I guess we're kind of in that regime where bending is quite easy compared with stretching. So we'll probably stay in sort of 3D embeddings of 2D surfaces for knitting. I think 3D knitting does exist-ish, but if you do an internet search, it doesn't actually come up with anything that's 3D. It just comes up with knitting machines that are really good at doing things like knitting a pair of gloves.
Still a shell.
Yeah.
So we actually have a jacquard loom across the street in textiles.
Have you seen it in action?
I haven't seen it in action, but
you have to go see it in action. They're insane. It's like it takes up like the whole room, and it's like everywhere.
Is this for like the sportswear stuff, or
no? This
why is it
there's
here?
like a textiles.
Huh.
If it's an emphasis. I don't know if it's its own department or anything.
I see.
But I took a tour over there, and they have one of these machines, like the programmable machines, and then they have a jacquard loom. And I'd gone over there because my first class that I taught was the physics behind the internet, which
cool.
It was like a 100 level class, and I was thinking like, is it information theory or what is this thing? Basically, it's like whatever you want, just kind of connect it to the information technology. So my favorite story was talking about the jacquard loom and how, this actually inspired the idea. It was a computer, and it inspired the idea of numerical computers.
Yeah.
And
you
then,
get to talk about like Babbage and then like ENIAC style, and it's pretty cool to look at the whole history of mechanical computation.
Yeah. The common thread. Sorry.
Yeah, that's a good story. I guess the other story that everyone loves to tell me is this. There's some story about Dirac like watching someone's wife or mother or something knit, and then it's like, madam, there are 2 types of knitting you're doing. And she's like, yeah, they're knits and pearls. They're related by this. And he's like, it's like, oh yes, this famous physicist has discovered something about knitting that like every grandma knows.
Yeah. Well, thanks again.
Thank you.
Visit.
Thanks.
Great talk.
Yeah, thanks for hosting me. And it'll be fun to see if I can actually make it out to Eugene sometime when we're not all dying.
Definitely.
Yeah, we'll make sure it happens.
Yeah.
Okay, we can go back to looking at counts of votes now.
All right. Have a good night.
You too.